Okay, let's get started. First of all, welcome to ReStructure 2.0 webinar series. This is the third appointment that we have. And just to summarize what ReStructure 2.0 webinar series is, this is, first of all, what's ReStructure? ReStructure 2.0 is a research project that is based at the Department of Civil Engineering of the University of Calabria, funded by the European Commission through the Marie Skłodowska-Curie Action Reintegration Panel, and I am the PI of this project. The idea behind this ReStructure 2.0 webinar series is to create an active network in which discuss about topics from the broader area of geotechnical earthquake engineering and to disseminate the research. We will have one webinar roughly every month. And for now, we are, the first three appointments are just a webinar, so only online connection, but soon we will have also in-person seminars, but the online connection will be always available. The presenters during this webinar series are worldwide experts in the broader area of geotechnical earthquake engineering. Today's host is Professor Jonathan Stewart from the University of California, Los Angeles, and I will give you an introduction about him in just a few seconds. But I just want to let you know that to be informed about the ReStructure 2.0 webinar series, you can subscribe to the newsletter. So you will get all the news about not only the project, but also all the events that we are organizing. And then you can follow the ReStructure 2.0 profiles on the social media. We have a Facebook, Twitter, and Instagram account. Let's go now on today's presentation. The title of the talk is Seismic Pressure on Retaining Walls Based on Soil Structure Interaction Principles. As you know, the speaker is Professor Stewart. For most of people, we don't really need an introduction about him because everyone that crossed his path with soil structure interaction for sure heard his name. But just to give a brief introduction, he's a faculty professor member since 1996 at the Department of Civil and Environmental Engineering at the University of California, Los Angeles. His technical expertise is geotechnical earthquake engineering and engineering seismology. The work of his research group has impacted seismic guidelines and policy nationally and globally. He has his research is included in the US National Seismic Hazard Model and a recommended procedure for the seismic assessment of structure. He's a former chief editor for the Journal of Geotechnical and Environmental Engineering and Earthquake Spectra. He currently serves on the ERI Board Directions, University of California Officer of President's Seismic Advisory Boards, USGS National Seismic Hazard Model Steering Committee, and co-chair of the year, among other positions. He is professional engineer in California, and he maintains an active consulting practice, advising private and government entities on the issue in geotechnical earthquake engineering. I had the honor to work with him during my period at UCLA, and I can assure you that he's really, for your academic, from the academic point of view, is really life-changing opportunity to work with someone like him. So that being said, thank you, John, for being here, for agreeing to give this seminar. And please go ahead and you can start your presentation.
Thank you very much, Margot. It's a pleasure to join you today. Buon pomeriggio, right? Buongiorno here. I appreciate the kind introduction. So are you seeing the presentation now in presentation mode?
Yes,
okay,
we are.
Perfect. All right, thanks for joining us today. As Margot mentioned, I'll be talking about seismic pressures on retaining walls. And I'll be trying to convince you over the course of the seminar that this is in fact a soil structure interaction problem and is best treated as such. I want to just acknowledge briefly those who have worked with me on this. So Scott Brandenburg, Maria Giovanna, also George Milanakis were direct contributors to what I'll show here. And a number of collaborators listed here have provided constructive comments and input as we've gone through this research in the previous years. I basically want to cover 4 topics. I'm going to introduce the problem. I'll talk a bit about observed Earth pressures, mainly from centrifuge experiments. Then I'm going to make the case, as I mentioned, that this is a soil structure interaction problem, and I'll talk about how we can model it as such. Soil structure interaction, if you've ever seen that in a class or followed literature on the topic, we usually separate it into its inertial and kinematic components. I'll define what those terms mean in this context and how they influence seismic pressures. And then I'll have some summary remarks. So by way of introduction, it's important to begin by acknowledging the fact that for the most part, retaining structures perform well during earthquakes, even retaining structures that have only been designed for static lateral loads, like from active earth pressures, for example, which was very common in the US for a number of years to not include a seismic increment. But there are exceptions. One notable exception that we see fairly regularly is when you have, say, quay walls along ports or other coastal facilities, and you have liquefaction either in the foundation or in the backfill. It doesn't turn out well. So liquefaction can compromise walls for sure. We also have walls that will fail if they are essentially masonry walls with very little moment capacity. It's not uncommon to see them having toppling failures during earthquakes like this one in L'Aquila. But despite this good performance, of course, we do in modern practice design walls for seismic loads. And there's a number of guidelines that talk about this. The one on the top is essentially the source document for the US Building Code. It's the ERP recommended provisions produced by Building Seismic Safety Council. This is where new innovations are brought into the code space. And then the formal code essentially uses language from the ERP. And then the NCHRP document is essentially the code that is used for bridges. Again, it's a federal document, and then it's adopted by different states. So in these documents, there's basically 2 options for how to deal with seismic earth pressures. One option is to do a direct analysis of the soil structure interaction system, which I'm schematically depicting here. You have a structure, and you may not necessarily have a structure next to walls. So this is there sometimes and not others. Sometimes they're freestanding. The gray area here, hopefully you can see my pointer, is the wall and the foundation itself. Then you have soil elements, and we basically can bring in ground motions at the base of this, and the soil will respond to those motions. It will interact with the wall and foundation. And if there is a structure, the structure will vibrate, and the whole system is analyzed in one big model. So this is done. So for example, locally here in California, we're building out a metro system in LA right now. And we have subway stations that look sort of like this without the structure going above the top of the ground line. And then there are structures all around. And so we'll build models like this in order to see what the impacts of an earthquake will be on those subway walls, particularly for the stations. So it is done, but it's not done routinely. Most walls certainly aren't going to get this level of attention. So for more routine use, we use so-called limit state analysis. And in the limit state analysis, it's very much like a static analysis. You have a wall, you have an active wedge behind. In the absence of an earthquake, you would have the self-weight of the wedge, a reaction force on the base of the wedge, and then the wall produces the active force that keeps this wedge in equilibrium. So that would be the PA. When an earthquake comes along, it's represented by a horizontal seismic coefficient, and you get an additional increment in the earth resultant PE, the wall resultant. So what we can see here with this simple force polygon is that when you have a seismic increment, this KHW, and there can be a vertical as well, it's making this vector longer. So there is an increase in the wall pressure as a result of the earthquake with these procedures. And this kind of concept has been with us for nearly 100 years now through the pioneering work of Wakabe and Mononobe and Matsuo. One of the relatively recent presentations of this limit state approach was by Koseki et al. 1998. And what they're showing here is this active earth pressure coefficient, which combines both the active and the earthquake increment in a dimensionless form. The horizontal axis is essentially related to the ground acceleration, the horizontal seismic coefficient. So you see when it's 0, you still have a force, that's the active earth pressure. And then as you go to the right, it's growing because of the earthquake force. One of the features of this, if you look carefully, is these different lines here correspond to different friction angles in the backfill soil. And they all start to go vertical at some point. So for example, for this middle one, if you get to a horizontal seismic coefficient greater than about 0.8, you essentially start to get an infinite force acting on your wall. And that is a feature of the solutions of this limit state problem. In order to resolve that problem, because we do certainly get peak accelerations beyond that level in seismically active areas, Seed and Whitman came up with a simplification of this so-called Mononobe-Wakabe method, whereby the seismic increments represented by a line given by this equation, they recommended it up to 0.4, but it's very often been used even beyond 0.4 for the simple reason that if you don't, you end up with infinite lateral earth pressure, and of course you can't design for that. Okay, so observed earth pressures. We can basically calculate seismic earth pressures or measure them using centrifuge models. And there's been a lot of work on that done over the last 10 or 15 years or so, mostly at UC Davis. Nick Sitar and various students who've worked with him at UC Berkeley, and University of Colorado Boulder, Shade Dashti with student Hushman have done these kinds of tests. And I'll show you an example of one. We can also do dynamic analysis and calculate the earth pressure from a soil structure interaction analysis. So I'll talk about each briefly. With the centrifuge modeling, what you have is a model of a soil structure system. There is no structure per se. The structure here I'm talking about is just the walls. This is one of the original ones at UC Davis, Alatik and Sitar, where they had 2 walls. This one was a fairly stiff wall in terms of its moment stiffness, the EI, and a more flexible wall here. These systems are U-shaped and there's soil underneath. That soil underneath is an important detail because it allows the wall to rock and to move because it's not rigidly connected to the bottom. And so each of the tests is going to have a different height of the wall. In this case, in prototype units, it's 6.5. 5.3 would be the half width down here. And then you have an overall depth that's much more. And they'll typically run multiple earthquake time series or sinusoids through these models. So the earth pressures in these experiments can be measured a couple different ways. You can put strain gauges on the walls, and by manipulating the data, you can derive the bending moment and then the shear and then the horizontal force that would produce what you've measured through the strain gauges. And that produces a linear variation of pressure with depth, which is indicated here under these strain gauge labels. And then you have discrete measurements with these so-called flexi force sensors that were installed between the wall and the soil. And so this is for one of the motions used in the test from the Loma Prieta earthquake. And whether you use the flexi force sensors or you use the strain gauges, and you see here different results for the stiff and flexible walls, you're getting pressures kind of in this range. If you use the Mononobio-Kabi limit state method with the recorded PGA, you get something bigger. That's this black line. So it doesn't fit. And so what you can do then to try to make it fit is multiply the PGA by a factor to reduce it until you get something that approximates the measurement. And so in this case, they've used 65%, and that seems to do a pretty good job. The trouble is when you go to a different ground motion, in this case, Kocaeli earthquake from Turkey, you have the same pattern that it's smaller than Mononobio-Kabi, but the 65% doesn't work anymore. So you would have to go to something more like 50% if you wanted to make it work in this case. And you can basically just continue this process, different motions. Each time you're going to need a different multiplicative factor if you want to match the data. So what we can see from this set of experiments and many others that followed it is that the pressures that are measured in these tests are smaller than the Mononobio-Kabi predictions. And like I say, this is fairly consistently observed. And so there's been different ways to try to overcome this problem. One of the more recent ones is to depth average the PGA and to try to use that to use as the input for the limit state approach. Okay, so another way of looking at the problem is to do a dynamic soil structure interaction analysis. There's been many studies that have done this kind of analysis. Typically, you have a rigid base, you have a wall that is rigidly connected to that base, and in fact, the wall is itself very often rigid, meaning the moment stiffness, EI, is infinite. And then you have an elastic soil behind. If you excite the base with some ground motion, the soil will respond. The wall will just be moving with the base. And so naturally, there'll be some differences and you'll get pressure exerted against the wall. And this is a few examples from one of these studies by Farhang Öztürk, where he is showing here the results of seismic earth pressure from different ground motions. So the different colors are basically different ground motions he ran through the model. And the Mononobio-Kabi limit state solution is shown here. And so you see in this case, the seismic pressure is actually much bigger than he was computing with his calculations. So if we summarize the observations for these freestanding walls, if we look at data from centrifuge tests, the pressures that are measured there are smaller than the Mononobio-Kabi limit state solution. If we do analysis of rigid walls and backfill soils on a rigid base, we get pressures that are much bigger than the Mononobio-Kabi. So we have two conflicting results here. And this has led to a lot of confusion where some folks say, well, Mononobio-Kabi is a bad solution because it's too high. And other people say Mononobio-Kabi is a bad solution because it's too low. What I'll try to argue as we go through is both of these sets of results are actually just fine. There's nothing wrong with the seismic pressures derived in either of those methods. The problem is that the Mononobio-Kabi solution is the wrong way to try to predict these pressures in the first place. To get it right, we have to account for the fact that this is a soil structure interaction problem and deal with that properly. So that's where we're going to go next. And what I'll be talking about, there's going to be a number of details as we go through this SSI-based approach, but there's a very basic concept that underpins the whole thing. And I'll just make that point up front, and you'll see this throughout. And that is that what really causes pressure to be exerted against a wall during an earthquake is relative displacement. It's really as simple as that. If the wall and the soil move together, I don't know if you can see me or not, but if one hand is the wall and the other hand is the soil, and they're moving together, there's no seismic increment of pressure. If one is moving relative to the other, the seismic pressure is changing. It really is just as simple as that. And you can get these changes from inertial and kinematic components, and that's what we'll be going through. Start with inertial. So inertial basically means you have a structure that is connected to the wall. from a practical point of view, this is when you have to worry about it. So I've depicted that here. There's a structure connected to this wall system. And the structure naturally responds. It produces base shear and moment. The base shear and moment, in order to get from the structure into the ground, is going to necessarily push the wall back and forth, and that will develop a reaction. Okay, so I think it's fairly obvious that a structure is going to do this, and that's going to produce pressures against the wall. So what really is the key detail in terms of modeling this is how connected is the wall to the lateral force resisting system of the structure. So I'm going to go through a couple of examples here. These inertial contributions are important when the lateral load path goes through the walls. So the case I was showing earlier, that is clearly the case. The walls are part of the lateral load resisting system. There's no ambiguity there. In a case like this, it is a little bit harder to figure out. This is a structure with a central core of shear walls that go right down to the foundation. And you have a separate foundation, perhaps for the walls, which may be off to the side. These dimensions from the main tower out to the sides can be quite large. These are called podium type structures off to the sides. And is there any transmission of the shear force from this wall out through these slabs to these perimeter walls? The answer is there could be, or there may not be. It really depends on the structural detailing. And so there isn't one simple answer to this. This is a case where the geotechnical engineer and the structural engineer have to talk to each other to figure out what the load path is going to be once you get to this ground line. And if there really is not a communication outward, then this becomes a kinematic problem over here. And then you don't have to worry about the inertial part. So how do we model it? Well, we can do the direct approach, like we talked about earlier, or we can do so-called substructure approaches. And I won't be spending time on this because it's well covered elsewhere. And it's not really the main focus of the presentation today. For the substructure approach for soil structure interaction generally, this NIST report is really the state of the practice, at least in the US, for how to do it. It's referenced in the building code, and by applying that approach, you will naturally work out what these pressures are from inertia. So we'll spend the rest of our time on the kinematic problem. And for the kinematic problem, I need to introduce a term here, which is the foundation input motion, or FIM. That's a kind of a standard notation that we use for ground motions on foundations due to kinematic processes. So let me explain here. We have a free field ground motion, which I'll call UG. The free field motion varies with depth. So here I'm specifying UG at depth 0, so the ground surface. We'll call that UG0. So there's no soil structure interaction here. This is the free field. Then we have a structure foundation over here. There's actually no structure, there's just a foundation. And the motion on the foundation we call the UFIM. Okay. And this UFIM can be different than the UG0 due to a number of processes. So if this UFIM is different from UG0, then the wall is moving in a different way than the free field, and we're going to get pressures from that. So let me kind of walk you through why that is, and hopefully make this help you develop an intuitive understanding of it. Let's consider first a free field condition. I have a mesh here. We have the total stresses acting on a soil element. There's no structure in this case, just a vertical and horizontal total stress. If I propagate shear waves through this medium, I get a ground acceleration at the surface and at the different depths. And if you studied wave propagation through soil, you know that in the absence of pore pressure generation, the vertical and horizontal stresses don't change. The only thing that changes due to this vertical wave propagation is you develop shear stresses, which are in dynamic equilibrium with the inertia of the elements above. So there's, again, notice no horizontal earth pressure is generated by this vertical shear wave propagation. Now, if I have a mass of soil that is an inclusion with that we can think of as sort of like a foundation, but this mass has the same mass density and stiffness as the soil itself. So I have kind of an inclusion here that's like a structure, but it has the same properties as the soil. Well, then naturally it will respond in exactly the same way as it did before. And again, there would be no seismic earth pressure. Now, if we make that inclusion have a different set of properties than the soil, so it's rigid in this case, and we send shear waves through there, now you get a different story. So the rigid inclusion cannot conform with what the free field soil is trying to do. It's going to displace in a different way. So UFIM will be different than UG. There'll be a little bit of rotation as well. And because this is displacing differently than the soil around it, there now is a change in the horizontal pressure along with the changes in shear. So this is where we get the seismic increment of pressure, differential displacements. So the key point is that seismic earth pressures are fundamentally related to the relative displacement. There really is no fundamental relationship between seismic pressure and acceleration. With and without the rigid inclusion, there's always been acceleration. What causes the pressure is not the acceleration, it's relative displacement. And that's an important point because, again, our limit state methods link acceleration with seismic earth pressure. And I'm basically arguing here that that is a fundamentally flawed link. It's not about acceleration, it's about relative displacement. So how can we model this? Again, the direct approach is great. There's, this is done for some projects, and there's absolutely nothing wrong with doing it. It is really the preferred way to do it if you have the time and the resources to do it. But we'll be focusing on simplified procedures, which is what we've been developing over the years to make this more readily accessible. And I'll kind of divide these simplified procedures into different cases with increasing levels of sophistication to deal with different aspects of the problem. So the simplest way to conceptualize this kinematic problem is this basic case where we have a rigid wall, uniform soil, and we don't deal with any inertial forces. And the nice thing about those assumptions, which are limiting for sure, but they do lead to a closed form solution. And I'll call that paper 1. You can then start relaxing some of those limiting assumptions, make the wall flexible, allow the foundation to be flexible, make the soil non-uniform, develop some inertia. You can deal with all of these things. It just makes the problem more complicated. And then you need a numerical solution. And finally, in order to really make this accessible and get it to a level of complexity that is similar to the limit state methods, even though the fundamentals are different, you can go to what we're calling a single frequency model, which is paper 3. So I'll cover each of these very briefly. Starting with the basic case, we have on the right here a U-shaped wall and a freestanding retaining wall. The red line represents a snapshot in time of the free field ground motion. And this free field ground motion has a couple of attributes. There's a displacement amplitude UG0, which is the displacement at the top, and it has a wavelength lambda. The wall and foundation itself are rigid, so the moment stiffness EI is infinity, and as such, the displacements of these can be represented through the UFIM, that's the translation at the bottom, and the rotation theta. So if I know these two, I completely know the displacement anywhere along these walls. The walls interact with the soil through springs, and the springs are represented through something we call stiffness intensities. So as engineers, we're used to springs. A spring represents the relationship between force and displacement. The stiffness intensity is a little bit different. It's essentially stiffness per unit area. So that if you then take the stiffness intensity, in this case kyi, and multiply it by a differential depth dz, and then a unit width out of the page, you get the stiffness for this spring. So it's kind of a convenient way to express it to start building models in the computer. So there's a horizontal stiffness intensity and a vertical. The way that this is solved, you basically work on the equilibrium between the reactions that form against the wall, horizontal and vertical reactions, and the reactions of the foundation slab, represented here by the capital letters K for horizontal and rotation. And those have to be in equilibrium with each other, both in moment and in horizontal force. Based on that, you can derive solutions for UFIM and theta FIM for a given UG0 and wavelength, along with the stiffness intensities. And that's going to give you a resultant wall force, PE, and also a moment. So just a quick note about the stiffness intensities. As I mentioned, it's stiffness per unit area of wall. We use Y for the horizontal, Z for the vertical. The units are force per unit length cubed. And these are related to the shear modulus of the soil. The horizontal is due to the horizontal reaction of the soil against the wall. The vertical is something we need as well. If we look at the red line here, it will rotate as part of these problems. And when it does, you develop a shear traction against the sides, which is why we need to have the vertical stiffness intensity. So the solution of this problem can be expressed as shown here. We have an ordinate, which is the seismic earth pressure resultant, normalized to get rid of the units. So the normalization is by the free field ground displacement, kyi, which is a constant because it's uniform soil with depth, and h. So this is a dimensionless force. And the horizontal axis, the abscissa, is the wavelength divided by the wall height. So you see that this peaks at about 2.3. There's kind of a complex back and forth at lower lambda over h's that we've just simplified to a horizontal line. And there's a resultant height, which is at about 2/3, more or less. The peak at 2.3, is at about 1 in this normalization. When you get to more than about 15 or so, you're seeing that this resultant force becomes very small. And we can actually derive closed form expressions to represent this normalized force and the resultant height, which I'm showing here. So really the critical finding here is that this interaction force is very strongly dependent on the ratio of wavelength to height. So let's kind of explore that a little bit further, because that's a very important concept in this whole problem, this wavelength effect. So going back to this schematic, we have the foundation and we have the free field response here. And I'm showing a case of a relatively low frequency with a long wavelength. And you'll notice that the variation of the displacement in the free field over the height of the wall is pretty modest. And under these kind of conditions, the UFIM and the UG0 are not so different. And there really isn't much in the way of rotation either. So this is a case where the wall is more or less moving together with the soil, and you don't get much in terms of pressure. So that would be the right end of that diagram with long lambda over h. On the other hand, when you have higher frequencies and shorter wavelengths, now you have an appreciable change in displacement over the height of the wall. This is going to cause these displacements to be different. There'll be rotation due to the differing displacements along the different heights, and you're going to get a lot of pressure developing against the wall. So that would be the left side of that diagram. So wavelength is certainly a first order effect in this problem. The simplified model, the initial basic case model deals with wavelength, but it doesn't deal with a number of other things that are also very important, which I've listed here: flexible wall, inertia, etc. And of these different effects, what we found is that the flexibility of the wall is really the most important of them. And in order to deal with that, you need a numerical solution of the equation of motion. A full frequency domain solution of this problem requires an input motion, which you can take the Fourier transform of and then solve it frequency by frequency. And by reversing that, you'll get a time series of wall responses. So we've developed these solutions. It's implemented in a Jupyter notebook, as indicated here, and can be used by engineers. You basically give the properties of the wall, the properties of the soil, the input motion, and it will work through the problem for you. This is something that Maria Giovanna worked on when she was here at UCLA. All right, so I'm going to just focus really on the wall flexibility part of this, which is the most critical. So the wall flexibility is represented in this not dimensionless. It actually has a dimension, but it's a normalized stiffness. It's essentially the soil stiffness, KYI, divided by the wall flexural stiffness. And then by taking the fourth root, you actually end up with something that has the units of 1 over length. We end up multiplying that by h to make it dimensionless. So the EI, I've just given some equations here. These are the standard equations for the stiffness of a cantilever. What we find is that the product of beta times h, which is dimensionless, if that's less than about 0.5, then this relative soil to wall flexibility, or stiffness, I should say, is such that the wall is effectively rigid. So just keep this 0.5 in mind. And remember, rigid is the baseline that we started with. But we don't usually achieve that in the walls that we actually construct. More typical values that you would get are more like 1 to 3, which is a more flexible system. And so this is an effect that we really need to take seriously. So you see here analytical solutions for different values of beta h. What we had before was 0 for the rigid wall. And as the beta h increases, the wall reaction force decreases. And that's quite an appreciable decrease. It's more than a factor of 2 reduction, for example, at beta h of 2. So it's a major effect. To help us understand kind of a physical level why this flexibility matters, let's take a look at this series of plots. Here we're looking at the ratio of the displacement to the free field displacement at the surface, UG0. This is dimensionless depth over the wall height, starting at 0, going down to the wall height. This is the soil response, the brown line. And the different colored lines are displacement responses of the wall for different beta h's. So a very stiff wall would be this one here. There's a large difference between the blue line and the brown line. So we expect a lot of pressure in that case. And then you see as the beta h increases, the wall is increasingly able to conform with what the soil is doing. So the relative displacements are smaller. So if you then look at the pressure that you calculate, we do see the largest pressure for the rigid wall. And as you go to more flexible walls like this red case, the pressure is getting much smaller. Okay, so finally, we have a single frequency model, which is the simplest way to account for these things. It simplifies the ground motion down to what's happening at a single frequency. So there's a single amplitude that goes with a single frequency. So this is meant for an analysis that has a similar level of complexity as the current limit state methods. So we're using essentially intensity measures instead of Fourier series in this solution. And we consider what are the most critical factors, which are wavelength over wall height, like we saw, and the relative wall soil flexibility. In order to make this kind of a tractable and usable solution, we make some approximations. We ignore inertia. We do use a homogeneous soil, and I'll talk about how we come up with the shear wave velocity for that homogeneous soil. We use linear properties for the soil, and we fix the base, as opposed to having a spring at the bottom of the wall. Of all these different approximations, the one that might be the most questionable in your mind is the linear properties. You know, we are talking about pressures that we're going to use in a design context, and in the design context, the ground motions are strong, and surely the soil is not linear. There's absolutely no question it will be nonlinear. So how can we have a method that uses linear properties? And I'll just mention, without going into a lot of detail, that there's two things that change when you go from linear to nonlinear. When you go to nonlinear, the wavelength gets smaller because the shear wave velocity gets smaller. And as the wavelength gets smaller, you climb that curve that we showed earlier, and it makes the pressures bigger. But the other thing that changes as you go from linear to nonlinear is the shear modulus reduces, the stiffness intensity reduces, and so you have two offsetting effects. And what we found through a lot of checking under different cases is they largely offset each other. And the additional complexity to include nonlinearity, which does really add quite a bit of computational effort, doesn't produce much change in most cases. So for the procedure I'll lay out here, we do use the linear properties to keep it simple. So I'll just walk through very quickly the procedure itself. We do a seismic hazard analysis. The intensity measure we want is PGV, peak velocity. We deaggregate the hazard, we get a magnitude and distance, and we basically use that magnitude and distance to get the other parameter we need, which is the mean period. That's the central period in a Fourier amplitude spectrum. We convert that into an equivalent frequency omega m, as given here. And this is a ground motion model for the mean period from Ellen Rathje and her group. So if you know the magnitude, distance, and site condition, you can come up with this. Now we need to represent the stiffness of the soil behind the wall. Typically, it's a sandy backfill. There's some variation of shear wave velocity with depth like this. We're going to take a time averaged shear wave velocity, which is the ratio of the wall height to the shear wave travel time, just like in a VS30 calculation, but now it's over the wall height, not 30 meters. In order to make this work, we have an equivalent ground motion amplitude, UG naught. So this is displacement, which we take as PGV divided by omega. So that's going to get it into displacement units. And then this factor F sub U was something that Maria Giovanna worked out by comparing more exact solutions to what you get from this simplified solution, and it's an adjustment factor to essentially represent a full waveform through these intensity measures. And so this adjustment factor uses the parameters we've just defined, Vs, Tm, and H, and varies from about 2/3 to 0.95. We have a stiffness intensity. That stiffness intensity, the solutions in literature are frequency dependent. Again, to make it simple, we ignore the frequency dependence and just use the static solution. And this is the equation for the stiffness intensity for omega equals 0. You do need Poisson's ratio and the mass density of the soil. We come up with a beta H, as we talked about before, so you need a section analysis to do that. Oftentimes, seismic pressures are being developed by a geotechnical engineer before the structural design is complete, so they may not know the structural properties of the wall yet. And so if beta H is unknown, an initial estimate in the range of 1 to 2 will generally be conservative. And then as the design progresses, you can always update it with the actual section properties. So with all of those things known, we're basically trying to use this solution that I showed you before that depends on lambda over H and beta H. And the way we do it is we have the equations for the rigid case, which you can easily put into a spreadsheet. And we use as the variable for the x-axis VS average times Tm over h, which is the same as lambda over h. So this goes into the equations, and then we modify it, the horizontal force, with this curve here, which we have an equation for, which is a function of the beta h. So this is where the wall flexibility comes in, and we also have an equation for the resultant height. And these are the equations here. I won't take the time to go through them. Essentially, these modifiers are just curve fits, and this is the theoretical solution for the basic case. These are normalized quantities, so we can denormalize the pressure resultant and calculate the moment as given here. So this is all pretty easy to put into a spreadsheet and start to apply. Now, we validated this against a number of the tests that I mentioned. So this is showing a number of the tests from Boulder in red, from Alatik and Sitar in blue, and then Ostadon's analysis in green. So you have the resultant force, lambda over h. The gray region here spans the range of beta h in those tests and analyses. And you're generally seeing higher resultant forces for the stiffer cases like Ostadon and lower ones for the more flexible walls. In order to look at this in a little bit clearer way, we take a residual, which is the measured resultant force divided by the predicted one. 0 would mean it's a perfectly accurate prediction. Negative means that you're over-predicting, and positive means you're under-predicting. There's quite a bit of scatter in these Boulder tests that is related to the data. But you'll see here that whereas the Ostadon results had been quite distinct from the centrifuge test previously, these residuals are all occupying about the same space now. This is doing a similar exercise with the Monmouth-Okabe limit state method using PGA. So you have positive residuals, under prediction for Ostadon, negative residuals, over prediction for the centrifuge tests, and you have many of the tests you can't even develop a solution for because of that asymptotic problem. If you use 0.65, there's a similar pattern. It does get better, but again, that just produces more under prediction here. You do a little better job here, and you still have undefined solutions at high PGA. So I'll wrap up now. Seismic earth pressures on walls are a result of relative displacement. I hope that I've convinced you of that. These relative displacements can happen due to inertial or kinematic mechanisms. Limit state procedures simply don't capture them. They aren't formulated properly to capture relative displacement, so they just don't work. The seismic earth pressure increment has no fundamental relationship to PGA, which is an underlying assumption of the limit state methods. The SSI-based approaches can capture what's been observed, and they do resolve these conflicting findings from literature, again, referring back to the centrifuge versus the SSI-based modeling solutions that we saw earlier. You do need to have a separate analysis for inertial and kinematic unless you're doing the direct approach that I discussed. And the single frequency procedure, that last procedure that I described, has been through a pretty rigorous review by practicing engineers here in the US. And it's incorporated as a NERHR Part 3 paper. So that's essentially a white paper that's in this building code related document. It doesn't mean that engineers are required to use it within the code. It's an advisory document, which is the way that all earth pressure documents have been treated in the code. There's never been a mandate. So now we'll start to see implementation of this, I expect, and I hope that this presentation will help maybe move that forward in Italy as well. So I think with that, I will stop, and hopefully we have a few minutes for questions. These are the papers.
Thank you, John. Thank you for the presentation. It's always a pleasure hearing your presentation. So if you have questions, we have time for a few questions. If you have some, please use the tool here. Okay, Gianluca, you have a question? Please go ahead.
Hi, can you hear me?
Yeah, I hear you fine.
First of all, thank you for the wonderful presentation, and I actually have many questions, so I will try to refrain myself. So actually, I have two curiosity, and I actually understand that most of this is a really hard topic. So my questions are not so much about going into much details, but about the curiosity of what you think it might happen. For example, you mentioned that for soil nonlinearity, I would expect that all of the things that you said are perfectly correct, but you didn't mention the damping of the soil. I was wondering, I understand that the relative displacement is what drives the problem, but if the relative displacement is the same, the ground motion is the same, and we have two different situations. One, for example, we have sand, and the other case we have clay, so we have different damping of the soil. Is the overall results in terms of earth pressure the same, or do you expect some differences due to the different damping properties of the soil? And the other curiosity is about, I think that the cases that you show, they were all about horizontally layered soils. I was wondering what would happen if we have inclined layers, major changes, or I don't know. So these are my curiosities.
Yeah, it's a good question. So if you go from sand, which is the typical backfill material, to clay, the biggest change is that you'll see a difference in the static lateral earth pressure. So we know that that would go up. The site response itself would change. Clay is usually going to have a lower shear wave velocity. And so that's going to shorten the wavelength. So that's going to, all other factors being equal, drive up the seismic pressure. So going from sand to clay would hurt you both statically and seismically. As to the damping issue itself, damping in the soil directly affects the ground response, right? The nature of the wave propagation in the free field. And so that would be the main effect. If you were to do a direct analysis of those two systems and somehow try to control for all these things, make the shear wave velocity the same and just change the damping, I do think you would see some difference between the seismic pressures in one case versus the other, like the radiation damping in the system and those kinds of things, and that interplay with the material damping would be different. My expectation is that would be a second order effect compared to everything else. I think the first order effects of a change in material type would be in the static earth pressure and the site response.
Understand, yeah, yes. Can you still hear me?
Now we can hear you. We lost you for a minute. Hello?
Yes, can you hear me? I don't, yeah.
Yes, we can hear you now.
Yes, and about the second question, if you would expect also differences if you consider not horizontally layered.
Oh, yeah, sorry, I forgot to answer that one. Yeah, if you have a more complex stratigraphy, the main impact of that would be on the site response. So I think my answer is similar. That would definitely matter. So you're going to have a more complicated site response. You're going to have a more complicated kinematic interaction problem as a result. Our simplified solution would not be able to deal with those complexities. So a direct analysis under that condition, would be able to deal with it. But if you have, say, a U-shaped wall and you have a very different site response on one side versus the other, our method really can't capture that.
I understand. Yes. Thank you very much for your answers.
Okay, thank you. Unfortunately we don't have time. We are at 6 p.m. so our hour is over. John, thank you again for joining us for this interesting presentation. And thank you everyone for joining. And I hope to see you soon at next webinar. You will be, I will send you some invitation as soon as we will arrange the next speaker. Thank you so much and have a good day.